Good morning, everyone, to this third set of PSYCHE guest lectures, for which we have two different speakers on today's program. Before we start, I would like to stress the following good practices. Please turn off all your cell phones, put your microphone on mute, and use the chat function for communication and questions. Our first speaker today is Professor Mirella Virginie from the University of Lille. She obtained her PhD degree in 2011 in the Strasbourg University in the field of catalytic tar reforming produced during biomass gasification. She acquired experience in the field of catalytic membrane reactor during her postdoctoral research for hydrogen diffusion after ethanol steam reforming. She currently is an associate professor in the UCCS laboratory in the University of Lille. Her research interests cover designing of heterogeneous catalysts for Fischer-Tropsch synthesis and dry methane reforming, biogas valorization, kinetic modeling, and effect of H2S as impurities. She is teaching general chemistry, biofuels production, and biogas valorization in Chemical Engineering School of ENSCL Lille. So, Mirella, the floor is yours.
Good morning, everybody. Thank you for giving me this opportunity to present a topic about Fischer-Tropsch process. So I'm Mirella Virginie. And here is the plan of the presentation of my presentation of today. So first of all, I will make a brief presentation of the UCCS laboratory. Then, as I talk about Fischer-Tropsch, I will start by a brief history of the Fischer-Tropsch process synthesis. Then I will go through chemistry of Fischer-Tropsch synthesis. So chemistry, it means I will talk about the products, I will talk about olefin, and I will talk about how this process occur in Fischer-Tropsch reactors. Then I will talk about catalyst design, and I will mention some important parameters for the catalyst design, that is support, active phase, promoter, and also about some specific catalytic conditions. Then I will finish by a few perspectives for the future in Fischer-Tropsch before I conclude. So I'm here today because I participate in the PSYCHE project. So the PSYCHE project, can you see the mouse on the screen?
Yes.
Yes. Okay. So the PSYCHE project involves plastic gasification in a vortex reactor technology. And then this gasification produces syngas that can be valorized by Fischer-Tropsch synthesis to produce base chemicals for the chemical industry. So in this project, we have base chemicals olefins, and we have a transformation of the syngas via the Fischer-Tropsch process. So it's what I'm going to speak today. I am a researcher in UCCS laboratory. It's quite a big laboratory, and this laboratory managed by different agencies like CNRS, chemistry school, that is now a school, an internal school of Central Lille, and University of Lille. And this laboratory lead research following three main topics, three main axes. And I am in the heterogeneous catalysis field. In this heterogeneous catalysis field, there are several teams that work on several subjects. And I'm a part of Catalysis for Energy and Platform Molecule Synthesis team. So this team is led by Andrei Kodakov, and the goal of our scientific project is to create and understand new catalysts and their performance in chemical reaction and processes in the field of sustainable catalysis. So we work mainly about alternative fuels, catalytic process, confinement, syngas, Fischer-Tropsch, olefin, and so on. Here is the website of the group where you can find more information if you want to know a little bit more about our subjects. In the UCCS laboratory, we have a lot of facilities for like spectroscopy facility, microscopy facility, diffraction and thermal analysis and so on. We have also a good equipment, RealCat. RealCat consists of a high throughput platform devoted to innovation and in heterogeneous, homogeneous biocatalysis. And this platform proposes a series of tools for the evaluation of catalyst performances, including parallel, continuous, and batch reactor and bioreactor. We have also the catalysis pilot hall, where we perform a lot of our experiment, and in this pilot hall, we could lead our, we can develop our micropilot reactor, working at high pressure, low to high temperature, in presence of security, because we use CO and hydrogen that are quite dangerous gases. So here is for the presentation of UCCS, my team, and the laboratory. And so I will continue this lecture by two questions. What is Fischer-Tropsch process and how to produce olefins? So let's talk about history of Fischer-Tropsch process. So as it is in the name of the process, it has been discovered by Franz Fischer and Hans Tropsch in the beginning of the 19th century, 19. Fischer-Tropsch synthesis is a technology that has an extensive history of production of gasoline and diesel from coal and natural gas. They developed their research in the Kaiser Wilhelm Institute for Coal Research in Germany. They discover that if they crack the coal by steam, they produce a synthesis gas that is a mixture of CO and hydrogen, and then they could convert this CO and hydrogen into liquid synthetic fuel. They do this process with cobalt, that means this catalytic process, and when they see that is really interesting, the commercialization of Fischer-Tropsch began around 1936 in Germany, and then through the world. So Germany, just before, I forget to say that they do this synthesis at pressure at about 1 to 10 atmosphere and temperature between 433 degrees to 473 Kelvin. Sorry. Germany has exported the technology, as I said, through the world to United States, Britain, Japan, France, South Africa, and also in other nations. So in Britain, the University of Birmingham was the pioneer in performing laboratory scale and pilot scale plan for Fischer-Tropsch synthesis. And then in the beginning was Germany and Great Britain, which were the most successful country, pioneer in developing the generation of liquid synthetic hydrocarbon fuel, Fischer-Tropsch technology. So during the World War, Fischer-Tropsch synthesis provide the needed liquid hydrocarbon fuels for the German war efforts. In South Africa, for example, facing to the isolation during the apartheid area, so Fischer-Tropsch catalyst synthesis known and will increase. And in United States, also, when there was the problem of the prices to the oil crisis, it started to be also interesting to develop this process. Here you can have a table that resumes the commercially established Fischer-Tropsch plant in the world. So you have the Fischer-Tropsch plant that are located in South Africa, in Qatar, in United States, Italy, in China, a lot of different countries in the world. And here you can have, you can see the date of the startup plant. So one of the older plants is located in South Africa and in Germany. And then here you have the feed and the product. So most of those plants use natural gas, coal, and produce Fischer-Tropsch liquid fuels and also methanol. Yes, the Fischer-Tropsch has been developed to allow the transformation of gas to liquid and coal to liquid. And the use of Fischer-Tropsch fuel is one of the prime reasons for global warming leading to climate change. So those feedstock, original feedstock, now has been a little bit, let's say that the Fischer-Tropsch process has been a little bit improved to other kind of feedstock like biomass, because biomass can convert syngas by a gasification process also. Using biomass to liquid is suggested to be a positive route to reduce the inclination towards fossil transformation fuel, and is also a key to keep the environment clean. So therefore, Fischer-Tropsch synthesis is viewed as a valuable process to produce super clean fuels from syngas derived from petroleum sources. To this, we can add also plastic, because in the PSYCHE project, our feedstock, the idea of our feedstock is plastic. So it's the same. Plastic can be used in gasification process to produce liquid fuels or other fuels, and then it participates also in a valuable recycling chain. Here I present a table of the actual biomass to liquid plant, and the first biomass to liquid plant was established in Ghent in Germany. And you see here they use biomass. Here you can see that all the biomass to liquid plants use solid municipal waste, forest, municipal waste, but all these are not source petroleum resource. So let us continue with the chemistry of Fischer-Tropsch synthesis. So syngas, so CO mixture of CO and hydrogen, is catalytically converted into a spectrum of hydrocarbon chain, including a fraction of oxygenate. So when we have the synthesis gas that is that go to the catalyst, so the molecule is adsorbed dissociatively on the catalyst, and then a molecule, an atom of hydrogen could meet an atom of oxygen, producing water. Up. An atom of hydrogen can meet an atom of oxygen, and then it will produce water. Here are the reactions of Fischer-Tropsch that can occur, and you see there's production of water. Also, an atom of oxygen can meet an atom of carbon, and then it will form some monomers, and the monomers on the Fischer-Tropsch reaction can meet some other atom of hydrogen, and then it will lead to the formation of methane. But one monomer can meet another monomer, and then it could form a short chain molecule like with 2 carbon, but other monomer can meet longer other monomers, and then we will have this option of longer chain. So here in Fischer-Tropsch we can produce alkane, alkene, alcohols and carbonyl, and here the number n can goes through 1 to high number 20, 30, 70, long chain. But in Fischer-Tropsch we produce water, but we have also the water gas shift reaction, which is the reaction our reactant with the water that is produced, and it will create CO2. And in Fischer-Tropsch, unfortunately, sometimes we have high amount of CO2 coming through the water gas shift reaction. So we have water, but we have also high production of CO2. And then also this reaction sequences, as I said, could produce methane and could produce longer chain. And this reaction sequences is called the probability of chain growth. And this probability of chain growth depends on different factors. Sorry. So different factors. Here we have the Anderson-Slurry model. On this model, we can see that we have different products that can be produced from Fischer-Tropsch synthesis, so methane, olefin, C5 to C11, C12 to C18, and C19. And so the chain growth probability can be can depend on the reaction temperature, from the hydrogen CO ratio, and from the catalyst composition. Sometimes, for example, if we put our target on a special window of products, for example, here, if we put our target on C2 to C4 products, we can see that these windows to have high amount of these products is quite narrow. It means that if, for example, the chain growth probability is lower, so we will produce mainly methane. And if this chain growth probability is a little bit higher, we are going to produce higher amount of heavy hydrocarbons. So depending of yes, the reaction temperature, to for example, if we increase the reaction temperature, we are going to limit the chain growth probability. And sometimes also, if we work with a partial pressure of hydrogen a little bit higher, we will also decrease also the chain growth probability. So it will also depend of the catalyst development. And so the development of selective Fischer-Tropsch catalysts, which can tune the selectivities to desired product, is one of the most challenging targets in the field of Fischer-Tropsch synthesis. So why we interest us to these C2 to C4 molecules? So these 2 to C4 molecules are called olefin, and the broad spectrum of derivatives results in a very diverse and market ranging from packing materials and synthetic textile and antifreeze agents, solvent and coating. So from those olefin, we can do a lot of different projects. Generally, they command significantly higher price than fuels, and they are used to produce intermediate chemicals of really high importance in industry. Let us to see that. Here is a table of the production of organic chemicals in 2010, so 10 years before. But yes, this table is really good, and it's difficult to find actually a good table resuming all this information. Things have changed a little bit, but not that much. So if we have a look on this production of organic chemicals, we can see that first of organic chemicals was ethylene. So ethylene is the largest volume petrochemical produced worldwide, and it is a carbon-carbon double bond, and it is one of the most important fundamental chemicals in the petrochemical industry, as it is a source of variety of products such polyethylene resin, ethylene glycol, vinyl chloride resin, acetic acid, styrene. So a lot of molecules that we know, and all those molecules are really used in packaging, textile and construction industries. We have also propylene. Propylene is an as important basic chemical as ethylene, because it has also a double bond with 3 carbon, and it is used to produce polypropylene resin, acrylonitrile, acrylic acid, and many other products resulting from different processes, oxidation, esterification, saponification, and so on. And then we have also butadiene. Butadiene, that is a double bond but with 3 carbons, and it is also a raw material for the production of different types of synthetic rubber. And these synthetic rubbers are in high demand all over the world, especially in Asia, for the manufacture of finished products in the electronics and automotive sectors. So this butadiene also can be used for gasoline blending components. So all those C2 to C4 molecules are really interesting target products and valuable products. So if we want to produce those olefins through Fischer-Tropsch, we have also to manage the reaction temperature and the technology to produce those olefins. So from the history until now, for Fischer-Tropsch synthesis, there's 4 main reactors that are operated over the world. Fischer-Tropsch reaction is a really exothermic reaction. So the design of the reactor is really important, especially to cool down the reaction. We can so differentiate reactor that works at high temperature and reaction that works at low temperature. So let's see a little bit the reactor. So we have the fixed slurry bed reactor. In this reactor, the syngas come from the bottom of the reactor and circulate through a mixture of hydrocarbon, where we have a mixture of hydrocarbon and the catalyst, and then it reacts to form normally long chain hydrocarbons. And here, through this mixture of hydrocarbon and wax, we have circulation of water for cooling, so to avoid this exothermicity of this reaction. And all the light products goes through the top of the reactor. We have also the multi-tubular fixed bed reactor. So it's a reactor with several small tubes. The syngas come from the top of the reactor and goes through all those tubes. And then those tubes are filled with the catalyst. and the liquid goes through the bottom of the reactor, and we have another exit for the light gas molecules. Then we have also the circulating fluidized bed reactor, where the catalyst is doing a loop. So it comes with the syngas, the catalyst, then we have the water as cooling agent, it reacts, and then we have the exit of the lighter gas molecules, and the catalyst goes through a cylinder to be recovered and continue this loop for the reaction. And we have the fluidized bed reactor, where we have a bed of catalyst. The syngas come from the bottom of the reactor, and it's fluidized with the catalyst, and produce mainly light gas molecule that is recovered from the top of the reactor. So we have those two technologies, circulating fluidized bed reactor and fixed fluidized bed reactor, that produce mainly gasoline and olefins. So for example, if we want to produce olefin, we are going to focus on those two technologies, but mainly working at high temperature Fischer-Tropsch, meaning between 300 and 350 degrees. So now we have our different feedstocks. We want to produce olefin, but which catalyst to use to produce the desired olefin at this working temperature for produce olefin. So let's talk about catalyst design. So the catalyst design, we have to, for catalyst design, to resume different property. So for a good catalyst, we should focus on chemical physical property, catalyst property, mechanical property. So we have to focus on the chemical state of the active phase. We have to focus on the support. We have to focus on the promoter, the size of active phase, and all those different parameters should be on the right proportion instead of to produce our desired products. So for support, so the support in supported catalyst, the support material usually represent the main component of the catalyst. So it is necessary to take into account the catalyst stability from the point of view of the active phase, and also support that has the same importance. So what we expect from the support, we expect a support for have a good dispersion of the active phase. So if we have a high surface area support, so it will lead to better dispersion of the active phase. We need also interaction between the active phase and the support to avoid, for example, sintering. We need a support that allows heat and mass transfer in an exothermic or diffusion limited reaction. The support should stabilize the active phase and sustain the mechanical strength for the catalyst. So for Fischer-Tropsch synthesis, through those later years, a lot of catalysts, a lot of support has been studied. We studied a lot of support like alumina, silica support, titania, zirconia support that are the main support used for catalyst. But also compare with this conventional oxide support, there's carbon materials like activated carbon, carbon nanofibers, carbon nanotube, mesoporous carbon, that also show interesting results in terms of mechanical strength, good electrical conductivity, high thermal stability, and large surface area. And so there is also other interesting catalysts like SBA15, hexagonal mesoporous silica, or MOF catalyst that has also interesting properties as they have high surface area, and it's possible to control the pore size of these supports. So in terms of active phase, usually in the beginning, the first active phase was cobalt, discovered by Hans and Fischer and Tropsch. Was cobalt, but then after they studied also iron. So iron and cobalt are from history the first active phase for Fischer-Tropsch synthesis. But there's also a lot of research made on ruthenium. Ruthenium is one of the most active catalysts for Fischer-Tropsch synthesis. It works at low temperature. But ruthenium is mainly for produce long chain hydrocarbon, and it's very expensive and limited in the world. So we are not going to use ruthenium to produce olefin. CO has good catalytic performance with a ratio hydrogen to CO that is quite high. It has good selectivity also to long chain paraffins. It is less expensive than ruthenium, but a little bit more than iron. But we are not also for synthesis of olefin going to use CO. There's also iron. Iron works very well at low ratio of hydrogen to CO, and it is interesting for production of olefin and oxygenate. It is really economic, it's abundant, even if in operating plant, iron is less stable compared to cobalt. I mean, cobalt catalyst has a durability of approximately 5 years compared to approximately 6 months in the case of iron. And there's also nickel that is quite famous. Nickel is very active, but it produces a lot of methane. And so nickel is not also really interesting for production of olefins. So to continue this presentation, I'm going to talk to you about 2 active phase. I'm going to talk to you about iron, that is a reference, but I would like also to talk to you about molybdenum, because molybdenum I've also shown some Fischer-Tropsch activity, not as high as a carbon catalyst, but it is interesting, and I want to talk to you about molybdenum carbide and molybdenum sulfide. So we study in our team molybdenum sulfide because it has some Fischer-Tropsch activity, and we would like to evaluate the activity of this support in presence of sulfur. And we have studied also molybdenum carbide because it's interesting due to its dual functionality of hydrogen dissociation and CO bond scission. So we studied those 2 interesting catalysts, and I'm going also to talk to you about iron, that is a reference catalyst, of course, and even through the active phase for iron-based catalyst has been linked to iron carbide. Different iron carbide phase are formed, which is still debating in the world research. But we are going to talk about those 3 catalysts today. So first of all, I would like to talk to you about the activation process of the catalyst. This is really important, activation process. So for when we have the oxide is not the active phase. So from the oxide, we need to form the active phase that will convert our syngas, hydrogen to CO, to our olefin. So to activate the active phase for molybdenum, to have it in a carbide phase, we activated under a flow of methane and hydrogen at high temperature for 2 hours to have our molybdenum carbide. For our sulfur catalyst, we use the oxide molybdenum catalyst, and we treat it on the flow of hydrogen and H2S to have our molybdenum sulfide at 673 Kelvin for 2 hours. And from our iron catalyst, we use CO as an activation process to have our carbide. So between 10 hours and 16 hours. Why to do this activation process? Why it is important? It is important because activation procedure will lead to the active phase. For example, with the iron catalyst, we use 2 activation procedures, one under hydrogen, one with CO. What we observed? We observed that we had kind of short transient period for both catalysts, but the catalysts which were activated with CO were stable with high CO hydrogenation activity and produced interesting olefin. In comparison, the catalyst that has been treated with hydrogen did not lead to the formation of the carbide phase, but the formation of metallic species. And then we observe an increase, slow increase in the activity, slow increase in the conversion of CO. And this slight increase of the activation of CO is probably due to the formation of carbide phase during time on stream. And of course, the activity of olefin were a little bit less. So activation process is really important to improve our selectivity to our desired products. So let's talk now about active phase and support. So for molybdenum carbide, what we observe, we use molybdenum carbide on different supports. And what we observe, for example, we have a lot of interesting conversion with carbon nanotube support. But if we have a look on the selectivity to olefins, we observe that we have higher olefin selectivity with molybdenum supported on alumina support. So we have better interaction between our active phase and alumina support, and it produces also interesting little quantity of methanol. So for molybdenum, it seemed that the best support with better interaction was alumina. We did the same with our iron carbide catalyst. We changed the supports, different supports, and we observed that we have interesting conversion with on carbon support. But when we have a look on the olefin selectivity, we observe that we have a little higher selectivity when we use the silica. So with silica, we had better interaction between our active phase and the silica support. So for iron, it seems that silica support is a little bit more interesting than mesoporous carbon materials. For this iron silica iron carbide based silica material, we are also study the effect of the size of the active phase. So we have here the pore size that been of the silica support that has been determined by adsorption method. We have also here the oxide size of crystallite determined by X-ray diffraction. And here we have the size of our iron carbide after reaction that has been determined by our transmission electron microscopy images. What we observe that there's a correlation between the pore diameter of the active catalyst with the pore diameter of the support. So here we have an increase of the pore size and an increase of our carbide phase. In reactivity, what we observed a high conversion for the catalysts that exhibit the larger particle size. And when we focus on the selectivity, we observe also high selectivity with molecule that has large particle size. So we also conclude from this study that when we have low particle size, probably we have less extent of carbidization, and when we have large particle size, we have probably better extent of carbidization that lead to high selectivity in olefins. So now I'm going to talk to you about promoter, because the addition of promoter can improve the selectivity to our target products. So the promoter could affect the structural or electronic property of the active sites. So I will continue my story about the three catalysts, and now I would like to talk to you about molybdenum sulfide catalyst. So for molybdenum sulfide catalyst, we have studied the effect of the promoter. So for our sulfide catalyst, based on alumina support, we observed that we have different production of olefins, rate of selectivity in production of olefin, depending on the promoter that we use. We observe with that we have better selectivity in olefin when we use potassium. So potassium is the promoter that favors the most the production of light olefin. So it was more interesting to continue our study with potassium and molybdenum sulfide catalyst. But which potassium? Because there are different sites of potassium. So we use different sites of potassium and we observe the effect of those sites. We observe that we have an effect because when we use potassium carbonate, we have higher selectivity in olefin than, for example, if we use potassium sulfate. We have nothing. When we use KOH, we observe an increase in C5+ selectivity. So further studies, we have done TPD CO2 TPD desorption to study the basicity of our catalyst, and we observe that when we have KOH, we have high basicity sites, and when we use potassium sulfide, we have two low basicity sites, meaning that for to have a high selectivity or interesting selectivity in olefin, we need to find a good balance between in the basicity of the catalyst. The basicity comes from the addition of potassium. So we have also observed the particle size on this catalyst promoted with potassium. For molybdenum sulfide is a little bit different. We have studied the layer, we have studied the number of layers, the slab length of the layer to determine the particle size. And we have seen that when we have large particle size, we have better conversion, better selectivity in olefin. So larger particle size improves the light olefin selectivity. Then, as potassium brings basicity, we also studied the potassium to molybdenum ratio, and we observed that there's an optimum ratio of potassium to add to have a good selectivity in olefin. So when we use too much of potassium, we decrease the selectivity of olefin. And this observation has been done for alumina support and also on carbon nanotube support, meaning that we need to have large particle size. We need to add potassium to increase the selectivity in olefin, and we have to put the right amount of potassium to improve the selectivity in olefin. We have also varied the conditions. We have seen that, for example, when we decrease the pressure, we increase the selectivity in olefins. And we have seen also that when we decrease the ratio of hydrogen to CO to 1, so we have less same amount of hydrogen to CO, we also increase the selectivity to light olefins. So to find good condition to produce olefin selectivity is really important on this molybdenum sulfide catalyst. So for condition, we need to work better at low pressure and with hydrogen CO ratio low also. Then now I'm going to tell you about the stem story with molybdenum carbide catalyst. What we observe with molybdenum carbide catalyst, we also studied the effect of the type of promoter. We have studied molybdenum carbide catalyst with sodium, iron, potassium, and nickel. And when we observe the conversion of CO, we observe higher conversion with nickel catalyst. But when we have a look on the selectivity, with nickel catalyst, we have mainly production selectivity of methane. That is not what we want. But when we have a look into the selectivity of olefin, we observe that we have higher olefin selectivity when we promote our carbide catalyst also with potassium. So the most potassium also here for molybdenum carbide catalyst is one of the most interesting promoter. Then also with potassium molybdenum carbide, we have varied the amount of potassium because before with molybdenum sulfide, we have seen we have an optimum. So here also we varied the ratio of molybdenum potassium, and we observed that when we increase this ratio, so when we had more potassium, we have a decrease in the conversion. So we have higher conversion when we had not too much of promoter. Then when we have a look on the selectivity into olefin, we observe that we have the conversion, the selectivity of olefin that increase with the reduction of the conversion. So at low conversion, it seems that we have higher olefin selectivity. So low conversion, we observe higher light olefin selectivity and also less CO2. So we study also the CO2 temperature program desorption, the basicity on this catalyst, and we also observe that increase in potassium content increase to the basicity of the catalyst. More we have basic site, less we have conversion, and less we have conversion also. Sorry. And we have also see by transmission electron microscopy images that we studied the particle size of molybdenum carbide catalyst, and we have seen that when we introduce potassium, we slightly increase the particle size of the molybdenum carbide. Just to remember, when we have low particle size, we have not high conversion and high selectivity in olefin. When we have larger particle size, we have better selectivity in olefin. So here, when we use potassium, it leads also to the increase of the size of the particle size, the increase of the particle size. We have also varied the conditions, studied different conditions with this molybdenum carbide catalyst, and we observed that when we have varied the gas hourly space velocity, when we decrease the gas hourly space velocity, we increase the conversion. And when we have a look on the selectivity, when we decrease the GHSV, we decrease the olefin selectivity. What it means? It means also, sorry, that with low conversion, we have high selectivity in olefin. And we vary the ratio hydrogen to CO, decreasing it from 2 to 1 at same gas hourly space velocity. And we observe that decreasing the ratio hydrogen to CO, we have an increase in selectivity in olefin. It's exactly the same tendency that we observe for the molybdenum sulfide catalyst. Then now I'm going to finish with carbon nanotube, iron carbide catalyst. With iron carbide catalyst, we study the effect of promoter, different kind of promoter in RealCat platform. And we have seen that the promotion with bismuth, tin and lead increase the CO conversion in comparison to the non-promoted catalyst. And then we observe that light olefins selectivity, the selectivity decrease when we increase the CO conversion. It's the same that we observe with molybdenum sulfide, molybdenum carbide catalyst. And also when we use another support that is carbon nanotube support, we observe the exactly same tendency with iron. And when we promote the iron with our bismuth or lead, we observe an increase in the production, an increase in the selectivity of olefin, but still the same tendency, even with the addition of the promoter, the selectivity decrease when we increase the CO conversion. We study also the effect of the pressure, and we observe that when we decrease the pressure on bismuth catalyst, so the selectivity also is improved. So now I'm going to, before to conclude, talk about some perspective in the Fischer-Tropsch. So some perspective has I've said Fischer-Tropsch catalyst was based on feedstock like coal, biomass, and natural gas. It's the formation of syngas, that is CO and hydrogen, to produce liquid fuels or olefin. And more people are interested not in CO, but in the hydrogenation of CO2. And CO2, we have a lot of CO2 in the atmosphere, a lot of process produce CO2. And then the idea now is mainly to valorize this CO2 via a Fischer-Tropsch process. For example, to use the hydrogen not only from gasification, but hydrogen coming from electrolysis of water. And it's the concept of what we call the power to liquid process. But this also for produce olefin from sources that is different than coal, biomass, natural gas. And for hydrogenation of CO2, iron catalyst seems to be the more effective than cobalt for this hydrogenation of CO2. Another perspective also, it's based on the reactor. A lot of researchers now are focused on microchannel technology that offer also new possibility for Fischer-Tropsch synthesis, allowing a highly compact unit that that increase the process intensification. Also, with this microchannel reactor, we have a better control of the temperature, and we have microchannel where we just fill the channel with the reactor, and now there are some researchers that try to coat directly the wall of the microchannel with the catalyst. So with reactor design, there's a lot of new challenges also for the production of olefin and improvement of Fischer-Tropsch reaction. And then there's also photocatalysis. Photocatalysis is also different reaction, but for example, here we use solar energy. We use also a catalyst, and it's also a promising way to valorize the syngas. So in our team, there's a researcher, Vitaly Avdomsky, that is working now on this topic of photocatalysis. So now I will conclude my presentation by resuming a little bit about my illustration. So Fischer-Tropsch process is a well-established process in the world that is coupled to a gasification system, gasification process. And it's really important relationship between structure and the catalytic activity of the Fischer-Tropsch process. It was, I tried to show you with molybdenum sulfide, molybdenum carbide, and iron carbide catalyst. What we've seen to have better selectivity in olefin, we have to choose the proper support, because the selection of a support enable the formation of the active phase and intimate contact with the chemical promoters. We have also to choose the right promoters if we want to produce olefin. So the adequate choice of promoter to increase the selectivity to olefin and minimize the methane production and higher hydrocarbons. We have also to pay attention about the size of the active phase. When we have too low particles, probably we don't go through high olefin selectivity. So we have to pay attention of the size of the particle, but also on the dispersion of this particle on the support. And then we have also to pay attention about the reaction conditions. So we have to work better at high temperature to produce olefin. We have to work better at low pressure if we want to use olefin. We have to be careful about also of the gas Hawley space velocity. And if we want to produce more olefin, it's better to work with hydrogen CO ratio at low hydrogen to CO ratio. It's what we also illustrated during this presentation. So to produce olefin, it's a fragile equilibrium, but there are still many challenges to try to find the good balance to produce olefin via the Fischer-Tropsch process. Here is a kind of a list of I would like to acknowledge my previous study, Chang Liu, Kang Chang, Tong Li, Bangu, and also the Alan Barrios, actual student, Daisy Perron, that is the postdoctorate. I would like to thank Andrei Kodakov, Vitaly Avdomsky, Robert Wojciech, and Christophe Dujardin, and also all the members of the PSYCHE Interreg project. And thank you for your attention.
Our second speaker today is Professor Yurai de Wilde from the Université Catholique de Louvain. He graduated from Ghent University in 1995 and also received his PhD degree here in 2001 after collaboration with Professors Gilbert Froment, Guy Marin, and Geraldine Hendricks. In the period of 2001 until 2005, Yurai de Wilde performed postdoctoral work at Ghent University and at Princeton University. Since 2005, he joined the Université Catholique de Louvain, UCL, where he is professor in chemical engineering since 2013. He currently also serves as president of the Doctoral School in Process Engineering of the Walloon Region in Belgium. His research expertise includes kinetic modeling, the use of dynamic methods, and the multi-scale modeling and simulation of chemical reactors, accounting for complex multi-phase flow patterns and detailed reaction kinetics. So Yurai, the floor is yours.
So good morning, everyone. So my talk will be on gasification and an overview of gasification and how it fits within what we try to do. I'll give a little bit of context to start with, then describe the main steps, focus on reactor technologies, say a few words about modeling and simulation, and then go into the specifics of plastic waste to end with an example of an industrial application. So the context is that we work on within the Interreg project here on trying to close the loop on plastic waste, and of course there are many groups interested in this at the moment, and many options are being studied, gasification being one of them. The other are listed here in this figure. Pyrolysis is an option, and it is often combined with reforming on a catalyst, aiming at producing mainly hydrogen then. And then if people even consider feeding to crackers, then there is gasification, either air gasification or steam gasification, and there the aim is to produce syngas or energy. You see an overview of different types of waste and an evaluation in terms of product quality, fuel quality, and so on, to look at the potential of those wastes. And here you see solid waste fuels, then wood waste, sludge, dried sewage sludge, and then here are non-recycled plastics. And then here are tires. And what you basically see is that plastic has some potential in terms of energy content. Another advantage is that typically the moisture content is very low, and the reference is coal. Yeah, coal is shown here, so which has 20 to 30 megajoule per kilogram. Then and here we are at 30, 40. The moisture content 3 to 10, we are at 0.2 with plastic waste. So there is some potential. There are some disadvantages, however, and that is mainly that there is some more chlor in it that you will have to deal with, and that will require either a pre-treatment or post-treatment. And then the same for a little bit of sulfur here, but still within acceptable limits. But it's mainly chlor that is a problem. So we are focusing on gasification, and let me show you here what the main steps are in gasification. You have to dry if there is water. Yeah? If there is water, and for example, for biomass waste, there is 10 to 20% of weight percent of moisture. That requires a lot of heat, in fact, drying. And then the first step is pyrolysis, which also requires heat, as we will see. You produce gases, liquids and oxygenated compounds. Liquids often referred to as tar. And then you produce typically a solid, char, which will play an important role later in the reduction. So those gas reactions, this is where the gasification reaction as such takes place. Yeah, you will gasify the char, and the gas phase components here and the liquids can also undergo cracking and other reactions at high temperatures. What you end up with is basically syngas But of course, conversions are not 100%. You will have some tars remaining, and that can be a problem. Those tars have to be removed. And depending on whether, well, if you go for plastics, you will have to deal with those other components, as I mentioned. So some more details about those different steps. So pyrolysis is, as you know, probably thermal decomposition in the absence of oxygen. It requires a lot of heat, and primary products are gases, hydrogen, methane in there, CO2, and then some C2, C3s, and then some condensables and char. And the relative yields of those products and the exact composition of that liquid that is formed, of that condensable that is formed, depends, of course, on the composition of the wood or the waste, but also on the heating rate, pyrolysis temperatures, and the residence time, and so on. So it's a quite complex operation to manage. Yeah? And often there are heat transfer limitations. Then the char, as I mentioned, will undergo gasification reactions. Again, a lot of heat will be required, and you see that you can gasify with steam, with CO2, and even with hydrogen, and then there is the water gas shift reaction here that will take place as well. But not all of those three reactions are equally important. Here are some relative reaction rates at 800 degrees C, and this pressure. And you see that steam gasification is much faster than CO2 gasification, and that hydrogen gasification with hydrogen is almost negligible in rate. These are the reactions. We are talking about a solid. The char is solid. That means that there can be transport limitations. You will form a solid particle, and you know that you can have different regimes. The extremes are that you have very fast diffusion inside the particle. Then reactions will take place inside the pores of the char. And you will have a uniform reaction rate. And the other extreme is that you hardly diffuse into the particle, and you will end up with what is called a surface reaction. Yeah. And then there is the intermediate situation in which you have a reaction rate profile in the particle. Those have to be accounted for, and depending on the reactor technology that is used, they will be more or less important. Certain reactor technologies will have bigger particles than others. Okay, that heat needs to come from somewhere, and that is from combustion, from oxidation, yeah? Combustion of the remaining carbon, but also of gaseous products. It can be done using either air, but then you have nitrogen that you introduce, which may reduce the calorific value and so on, or you can use pure oxygen. It also has an effect on the temperature, the maximum temperature that you will reach in the reactor, and hence on the slug, on the ash formation, will the ash melt or not? But anyway, combustion products, you know, and they can serve as gasifying agents eventually. Yeah? So the reactions are shown here. Carbon can react to CO2, CO to CO2, and so on and so on. Yeah? And tar can also be partially combusted. So that's what makes the control of a gasifier somewhat difficult, and there is the coupling between the heat produced from the products of the pyrolysis and the reduction reactions, the gasification. Yeah, the heat produced here must compensate the heat requirements in the gasification zone and the pyrolysis zone and for the the drying zone, and so that heat produced here depends on the products of those zones. Yeah? So there is a coupling. An important parameter is the equivalence ratio. Yeah? They call that equivalence ratio. It's the amount of oxygen to fuel compared to the stoichiometric requirement if you want to combust everything. Yeah? And so they work depending on what waste type they can give you optimal equivalence ratios to operate. The effect of the equivalence ratio on mole fractions of different components here is shown for wood gasification. And you see obviously that as you go to very high equivalence ratios, you start combusting everything and you end up with CO2 and steam. This was air gasification, by the way. Yeah? You see how the nitrogen content increases as well. But you end up with, and so you see if you want to produce maximum CO, for example, and that there is an optimal equivalence ratio, and the hydrogen concentration will gradually decrease. Yeah? Of course, this is the concentration, the amount you have to look at, that's another story. Yeah? But you see that there is an optimum at a given moment. You start just combusting too much. So now you have to manage these three reactions in the best possible way, and looking at the different constraints, and depending on which of the aspects is the most limiting, you can choose different reactor technologies. Yeah? And the aspects that can be limiting are various. They can be purely technical or economical. You may look for a technology that is very flexible with respect to the feedstock, or you may really have a given feedstock for which you want to optimize operation, and for example fine particles or very big particles. So depending on what your situation is, you have a choice of reactor technologies that have been developed. By the way, most of those technologies have been developed, I didn't talk about it yet, for coal gasification, of course, so this is a very old technology. And so for coal gasification, the reactions are similar. You devolatilize the coal, that's the first step, and then you have also reduction reactions of the carbon that is remaining, and you have oxidation reactions. Okay, so looking at the reactor technologies, there are fixed bed, moving bed technologies. Well, it's in fact a moving bed. It's a fixed bed that is slowly moving down as particles react. Yeah? Then you have fluidized bed technology and train flow technology. I will show what that means in the next slides. Rotary Kiln, moving braids, and plasma technology, which is modern. Some commercial suppliers of those reactors are shown in the right figure here. Depending on what capacity, it's not only one of the constraints is capacity, of course. Depending on what capacity range you are looking at, your choice depends also on that, and you see that fixed bed downdraft gasifiers, and I will show what that is, are really handy small scale, preferred small scale. When you go to larger scale, you go either updraft fluid or fluid bed, and then in train flow is for very large scale. Yeah, that's roughly what the situation is. So concerning fixed bed, moving bed, it's in fact a relatively simple technology. You all had the coal stove at home with your grandparents at home probably. it's a little bit similar. Yeah? But there are two. And so the advantage of the simplicity is that even at small scale, it is economically viable. The cost is sufficiently low. Yeah? There are two main types, updraft, downdraft. So updraft is countercurrent, and the particles are always fed at the top and move under the action of gravity downward. Yeah? And so if you go down in downdraft, you are co-current, in updraft you are countercurrent. Yeah? Now if we look first at that updraft situation, yeah, you will feed the air or the oxygen at the bottom here. They would, or let us look in the direction of the particles. Particles come in, they dry. Yeah, they dry using the heat from the gases that go out. Then they come into a pyrolysis zone. Yeah, they use the heat of the gases that come from the gasification zone. Yeah. So particles then move to the gasification zone. Yeah. The remaining, and that is, so this is the Gar. The Gar moves to a gasification zone, and here the Gar is gasified, and the remaining Gar, you need heat, and the remaining Gar is combusted, where you generate the heat, and that heat is with the gas flowing upward to the gasification, pyrolysis zone, and so on. So the heat comes from here and moves up, and the combustion zone also generates CO2, H2O, which can be used for the gasification of the Gar. That's the whole idea. So it looks very logical. The only problem that you have here is that in the pyrolysis zone you produce tar condensables, but they are of course gases, so they are entrained. They go out of the reactor and then will condense later and cause a lot of trouble. So you can do some post-treatment eventually of the tar, cracking or whatever, but that's a problem. And so that was the reason why downdraft operation was invented. Here you have something else. Your feedstock goes down again. They enter first the pyrolysis zone, yeah? And then just below that pyrolysis zone is the combustion zone where you inject air. Yeah? And the gases go downward. Yeah? They go downward. The pyrolysis gases go downward. There is combustion here of part of the Gar and part of the pyrolysis products. Then you go into gasification zone where you do the reduction of the Gar and produce a max of syngas that goes out. Yeah? The advantage is that the pyrolysis tar here goes through a high temperature zone and will be cracked. Yeah? You will have a lower tar content in your gases. Disadvantage of this is that as there is a downward motion of the gas, the heat transfer is the heat exchange between the combustion zone and the pyrolysis zone is a little bit less efficient. Yeah? And here the heat is going up to the pyrolysis zone. Here it is the gases are going downward. You see that in the temperature profiles that are shown here. There is here, of course, the highest temperature is at the combustion zone, yeah, in both cases. But here the gases move upward through the gasification zone and carry with them the heat. Here it's not the case. Yeah? So you have a steeper temperature gradient. So to finish on fixed bed, moving bed technology, here is a slide on coal, by the way, showing exactly similar temperature profiles. This is a downdraft operation. So equipment efficiency is generally high, and you can work with relatively low oxidant requirement. Those units are typically operated at low or moderate pressure, and you can use relatively large particles as feedstock. Yeah, so the feedstock preparation is less complex. On the other hand, there is a limited ability to work with to handle fine particles. They would plug the bed, and this bed has to be kept in motion, as you know. So in general, the feedstock has a quite long residence time, but it depends a little bit on the feed size distribution. You need to give that the necessary attention, the feed size distribution, and of course, yeah, you can control the operating parameters like the flow rate and so on. Then there are, as I said, two ways of operation, and it also depends on not only whether you use air or pure oxygen, but how much steam you use. You can work with dry ash mode, where the ash is removed as dry ash, or when you operate with less steam, in slagging mode, where the ash will be melted and you remove it like that as a slag. That steam content, of course, will affect the hydrogen to CO ratio in your syngas. So flexible technology in terms of feedstock in general, but the moisture content will have a big impact on your discharge gas temperature. Especially in those updraft, because the drying consumes a lot of energy. Yeah? Okay. The next technology is fluidized bed, where there are again different options. You know that fluidized bed is a technology that covers a wide range of regimes, and so there is the bubbling fluidized bed that is used in practice, or circulating fluidized bed, where you entrain the particles and circulate them around. In general, fluidized beds are known for their efficient mixing and the temperature uniformity. So feedstock will be immediately mixed with already, in a bubbling fluidized bed, feedstock will be immediately mixed with already reacted solid. Typically you work with a bed material, an inert bed material, yeah? Sand is often used, and for the rest the bed material will be mostly char. Yeah? Again, because of the presence of this inert and the temperature uniformity, you have a quite high tolerance on the fuel quality, and there is big thermal inertia in the bed, which explains the stability of operation somehow. Yeah? Okay. Bubbling fluidized beds, there are again two types. You can work at relatively low temperature, below 900 degrees, to avoid ash fusion and related agglomeration, or you can work at higher temperatures. That is done if you want to produce, if you want to minimize the production of CH4 and other hydrocarbons. It gives you, in general, a better quality gas. Yeah. Then, well, fluidized beds are always operated relatively low pressure, 1 to 10 bar max. Then circulating fluidized bed. In circulating fluidized beds, the particles will be circulating, and they will be, here the particles stay not in the bed, here they will be entrained with the gas. The bed density is much lower in general, and you have relatively long residence times. Particles will leave with the gas, so you have to separate them here in a cyclone and then just recycle them back if they are not yet converted, and the innards, of course, will also be recycled back. Other advantages, here you see a typical temperature profile for the gasification of biomass in a fluidized bed, and you notice the temperature uniformity. Here you feed the biomass, and very quickly throughout the bed you have quite uniform temperature. Well, yeah, and that's also interesting to see here. So of course, as the steam, air or oxygen comes in, you first have a combustion, and that is followed by the gasification. Okay. So you have the fluidized bed has a high load flexibility, high heat transfer rate, so I already said high feedstock flexibility, moderate oxidant and steam requirements, and it operates at a uniform and moderately high temperature. I said there are two types, but that's well. So the moderate is for the low temperature bubbling fluidized bed. Okay, but it requires quite some hard recycling, and so the cyclones are quite charged. Then entrained flow reactors were developed for very high capacity power plants. Yeah. Here you see an downward, because you have entrained flow upward or downward. Here you see an entrained flow downward reactor. The coal and the steam oxygen or air are injected at the top, and the gases leave here, whereas the slag is removed at the bottom. Yeah. Again, the temperature uniformity is quite good, but it depends a little bit on what feedstock is used. This is here for coal. You have, on the other hand, quite large oxidant requirement, and you operate at very high temperatures. Yeah? A characteristic of entrained flow is that you operate at very high velocities and extremely turbulent flow. And particles are typically also quite small, so you have a very rapid feed conversion, and because of that you can have a high throughput. The residence time is only a few seconds here, but anyway, yeah? And you can feed that feedstock dry or as a slurry. Of course, if you feed it as a slurry, you have to evaporate more water, and logically the thermal efficiency of the apparatus decreases. Yeah. So the conversion is very high, but the efficiency depends a little bit. Okay. Then, because you work with such a high temperatures, you can produce a tar-free syngas, and the pyrolysis product will be, the tar that is produced will be further decomposed. Yeah? And also because you work at such high temperatures, the ash is typically melted into this slag that is removed. Yeah, these are other figures for entrained flow, upflow, downflow for biomass gasification, but nothing to say here in view of time. Then other large-scale technologies that are frequently used are the rotary kiln and the moving rate reactors. Yeah. The rotary kiln is shown here. Yeah. It's slightly inclined towards the discharge point here, and it has an independent control of the axial speed by means of the rotation. Yeah. The rotation speed will control the axial speed. And so that gives it quite some flexibility. Yeah? This can be used with a wide variety of feedstocks, and that means particle size can vary, the moisture content can vary, and so on. You can just adapt the axial speed very easily, and so on. The major challenge then becomes the flow control of the oxidizing medium, because you want to avoid a too high temperature here. When you burn everything too locally here, you would have an excessive temperature. So what they do is they design systems that distribute the air over the entire length over the rotating kiln in order to prevent those hotspots. A moving rate is shown here. The fuel is put on a sloped moving rate, and the oxidizing medium is in fact on both sides. But for the rest, it's gasification in 3 stages. You have drying, pyrolysis, and gasification. Where exactly those 3 zones will be located within this furnace here, where exactly they will be located within the apparatus, within the gasifier, that depends a little bit on the fuel characteristics. So the zones can physically, their position will shift depending on what is used. But this is again very flexible in terms of feedstock, and it provides long residence times, which can be important for larger solid fuels. With plastics, there can be a problem with the feeder because of plugging. Plastics have a low softening temperature, so they can plug the feeding system here. But that is plastic feeding is a general problem for all technologies in general. Okay, then a last technology that I wanted to show is the plasma reactor. What makes it very distinct is that you operate at very high temperatures, and you provide the energy through power. So here you see a figure of that, and you have a plasma torch, and here the gasification takes place. The slag can be removed at the bottom, and the syngas typically moves out at the top. So the temperatures are very high, and despite that, you would say, oh, you consume a lot of energy, but the thermal efficiency is quite high. About only 2 to 5% are actually consumed of the total energy are actually consumed for the plasma torch. The rest goes really into the syngas. 80%, the rest 80% goes into the syngas. You have to, of course, take care of heat losses at those high temperatures, but you can have relatively long residence times, and you form no tar, because at those high temperature tar products are cracked. You also destroy toxic components like dioxins and furans and so on, so that's a big advantage. No char, ash or residual carbon. You only produce this slag, glassy slag, and you can have extremely high conversions. It's also insensitive because of the high temperature operation to the feedstock quality. Not only because of the high temperature operation, but because you supply the energy through power, which is an independent energy source. And in all other technologies, the energy comes from the combustion of your pyrolysis and gasification products. So that's the coupling. Here you have an independent energy source, and that gives you much more flexibility with respect to the feedstock. Okay, the rest is about compliance with emission standards, well, there are 2 aspects that are often used to question plasma reactor technology. One is the scale up. Generate large plasmas is indeed challenging. So that is one thing, and then the cost. But the cost, there is discussion about the cost. The power is of course a cost, but with all the green energy that will be produced in the future, that should not be a major problem. Yeah, this is a summary of characteristics of those different technologies in terms of what is the acceptable particle size, what is the acceptable moisture content, what is the ash content, and so on. Yeah. Bulk density, also very important in terms of reactor size, of course. And you see that fixed beds are, of course, or moving beds have the highest bulk density, together with those moving grades. The rotary kiln has more void, and the bubbling and circulating fluid beds have, of course, a much lower bulk density in the plasma reactor as well. Then there is a section on the tar content, which is, of course, as I said, lower in downdraft gasifiers and in plasma reactors, and problematic in the other types of reactors. Yeah. Okay, but in view of time, I think I will not rediscuss everything here. Well, one slide about modeling and simulation, because you cannot discuss the details in 50 minutes. You have to address all the aspects, and that goes from reactions. The kinetic modeling can be gas phase reactions, liquid phase reactions with molten plastics, solid phase reactions. They all have to be dealt with, and you can deal with them at various levels of sophistication, and going from global reactions to reaction networks. Mostly people use global reactions, but there is more and more incentive to work to go into more detailed description. But the problem is that you need to characterize also your feedstock. And with wood, this is going on. This is indeed happening. They characterize the wood in more and more detail, and describe the reactions for the different components in more and more detail, and with plastics waste as well. But then you have to measure the intrinsic kinetics, and that's also not so evident. When you measure intrinsic kinetics, you, in theory, have to do that in the absence of transport limitations, and it's also a transient. Gasification is transient, so you need a time accurate. Typically, you do transient experiments and to study the reaction kinetics, but you need fast gas analysis. So it's absolutely not obvious to measure the intrinsic kinetics. Apart from that, when you want to simulate a commercial reactor, you will have to deal with those potential intraparticle mass and heat transport limitations in the GAR, or with interfacial mass and heat transfer limitations between the gas and the particles. And then, yeah, you will have to deal with the flow pattern. In moving beds, you can generally assume plug flow, but the other technologies that we have seen, it's way less obvious. Fluidized beds, there are some engineering models for fluidized beds that can be used, but people now turn more and more to CFD, computational fluid dynamics, where they try to simulate the flow pattern in 3D. And get 3D details of composition, temperature profiles, and so on. So again, those CFD models, there are many various levels of, there are many levels of sophistication possible. A lot is related to the way you will describe or account for the effects of turbulence. Yeah. And then for multi-phase flows, yeah, also the detail in which you want to describe those different phases. For example, if you have a particle, a fluidized bed, you can describe the solid phase as a continuum, and so or you can really track individual particles, or you can do something in between, track pseudo particles that represent each pseudo particle represents various real particles. So various levels of sophistication are possible, and each of them has advantages. But typically, the higher the level of sophistication, the higher the computational time, and so that's the trade-off you have to make, especially if you want to couple this with the reactions. And then there can be radiation that you have to account for as well, which further complicates things. Yeah, then a few words about plastic. We all know the problem of plastic. Not the problem, we like plastic, it is an incredible product, but we produce more and more of it, and that means we dispose of it more and more. And yeah, those graphs speak for themselves. The lifetime distribution, well, it's not unexpected. It's mainly packaging that has a very short lifetime, but the other plastics also have relatively short lifetimes, and then you have to do something with it, or you pile up the waste. So the idea is to try and use existing technologies to close the loop, and you can of course mechanically recycle, but that has limits. Yeah, you can only do that a couple of times, and the quality is gradually reduced. So the chemical recycling is really aiming at producing virgin polymers by starting again from the building blocks of the polymers. You break down the waste to the building blocks and start over again. Yeah, there is a positive evolution in recycling, negative evolution in landfill, which is a little bit discussed at the moment, because if you want to reduce CO2 emissions, burning for energy recovery the plastic is not the best option. You see that people are burning more and more plastic and recover at least the heat, the energy. But that of course leads to CO2 emissions. But you can argue that if you want energy, you will have CO2 emissions anyway. But landfill is of course the easiest option to reduce CO2 emissions. But closing the loop is what we aim at. It's a little bit more complex, and so plastics are complex. Yeah, are simple and complex in a way. They are complex because of this. Yeah, because of additives. Pure polyethylene would be relatively easy to deal with, but and would be even more easy to deal with than certain vacuum gas oils, but those additives, dyes and glues, they make it a little bit more difficult, and so you will have to do either a pre-treatment or a post-treatment, and that's what we are also working on, Steven de Meester, in this project. Another problem with plastic is this: you produce relatively, and that is then specific for gasification, you produce relatively few char. Yeah? We compare here, maybe let us look at this graph. This is a result of the volatilization at a given temperature of coal. Yeah? then peat and wood, biomass, yeah? And then of plastics. And you look at how much percent ash is produced and char is produced. And the char is important because it goes to the reduction zone. Yeah? And you see that with coal, yeah, you have a huge amount of char that is produced. Yeah? Well, the numbers are given here, in fact. And with peat and wood, still a big amount. Yeah? But once you go to plastics, except for PVC, there is nothing. Yeah? So you hardly produce char, and so you can wonder what there is to gasify. Concerning the ashes, very little, and when they are ashes, they are typically related to color agents that were used or whatever, yeah? Printing agents or color agents. So the gasification technology has to be a little bit reinvented because of very different pyrolysis product distribution, yeah, with much less char. Yeah. But people continue to work on this and focusing then mainly on the pyrolysis. Yeah. And so more and more there is people gain insight in the pyrolysis products of propylene, polyethylene, polystyrene, PETs, and so on, how they form those primary products and also eventually non-wanted products, yeah, like tars. Yeah. That depends, of course, on the severity of operation, and the higher the temperature, the more risk you have of formation of those tars, and on the residence time. The longer the residence time, the worse the risk as well. And so more and more detailed characterization of pyrolysis products is done, and that allows to develop detailed kinetic models that go a little bit further than the lumped kinetic models that are shown here. So typically, and that's also in biomass gasification, people use lumped models where you go from your plastic, yeah, to something that is called gas with a composition that you have to provide. If you want to simulate it, you have to provide the gas composition. It has to be measured, and it will be function of temperature and of course of the waste that is used. And then your liquid, condensable, again with a certain composition that you will have to measure and impose in the simulation code, and it will be again function of temperature and so on, yeah, and char. And then that goes to other products in the next step. So those lumped kinetic models are very popular, and people simply measure at different temperatures the composition of their lumps. And the problem is once you start to mix wastes. Yeah, once you start to mix waste products for gasification, two different kinds of plastics or anything, you cannot just add up the resulting gas composition. It's not a weighted average of the two gas compositions of the two primary products that you used. It's not like that, because those different components will react with one another, and they will interact and react with one another. So at that moment you need a more fundamental description, and that is done by developing reaction networks and looking really at the elementary steps of the molecules involved. Yeah? And that requires network generation, and of course also determining the rate determining steps and the rate parameters, which have to be yeah, some are estimated from experimental data. So there are several groups working on it. The reference is given below. Yeah, so let me skip this slide here. Okay, so then industrial application of plastic waste gasification. There is one slide. In fact, there is some progress. Yeah, there is some progress. There are some companies, and there is an example here of Ibarra, who uses pressurized internally circulating fluid as bed. There are so two. There's an it's an internally circulating fluid as bed, and they carry out gasification in two steps: low temperature, high temperature, and the high temperature is there to avoid dioxins formation from the plastics. And because of the high temperature operation, they have to remove the slag. They can remove it as a molten slag. Yeah? The ash can be removed as a molten slag, sorry. And that can be reused in the cement industry and so on. This facility has been operated since 2003, capacity of 195 tons per day. And the syngas produced was used for ammonia synthesis. Yeah? And based on this, there will be now a first plastic waste gasification recycling plant. The feasibility study is underway. It will be built at Showa Denko Kawasaki plant. No, at the GCC. It will be built in South Korea. I don't know exactly where, but the capacity will be several hundreds of tons per day. Yeah. Okay, I had some slides here, backup slides, but I don't think I will have the time, and leave some time for questions eventually. So gasification is in fact a well-known technology in the industry, coal and then later biomass. But so now there is a renewed interest. A few years ago it was because of biomass, and now because of plastic waste. There are various reactor technologies, and the optimal choice, there is not an optimal reactor. It really depends on the application, meaning the feedstock and what you want to do with the syngas and so on. And as I showed, plastic waste gasification has some specific challenges. That's why there is still research going on in this field, and also in terms of optimal reactor design. There are some first commercial applications reported. Voilà. With that, I would like to thank Interreg for the financial support, and I would like to thank our partners here for the very nice collaboration, and I thank you for listening.
Thank you, Yurai, for the interesting presentation. There are some questions in the chat. The first question: is electrical heating an alternative for combustion heating?
Yes, we are in fact considering that. So the project is I didn't talk about our project. In fact, I didn't think it was the objective of a lecture. But the objective of our project is to develop an efficient and sustainable reactor technology, and electrical heating is considered in there. Yeah. And as I said, in plasma reactors, it is already electrical supply. But our reactor is not plasma reactor. It is, but electrical heating is considered. Yeah.
Okay, a second question: can GO gasification of plastics with coal improve charge generation?
Yeah, of course. People consider mixing biomass and coal with the plastic, so that is being studied, yeah, and reported in the literature. Yeah.
Then a final question: are fluidized bed technologies fit to handle sticky plastics?
I would well, if you look at the temperatures, the plastic will indeed be molten, and it all depends on the agitation of the bed. But I would not recommend it, to be honest. I would not recommend it.
Okay, thank you again, Yurai, for your presentation. To end, I would like to thank both Mirella and Yurai for their interesting presentations and all of you for participating to these guest lectures. I would like to acknowledge the funding received from the European Regional Development Fund via the Interreg France-Wallonie-Vlaanderen program, together with funding from our local authorities, being the provinces of West and East Flanders, the Walloon Region and Walloon Public Service on Economy, Work and Research. So thank you all for being present, and I wish you a nice day.